Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. We have been discussing alkene and alkyne oligomerization reaction in the past few lectures. In this context, we have covered two main reaction. One is alkene ethylene oligomerization, alkene and alkyne oligomerization, and in this context we have covered two reactions. First one is ethylene oligomerization, this we have covered from the perspective of SWAP process. SWAP is shell higher olefin process. And this we have covered using the nickel catalyst. Nickel hydride is an active species for the catalyst for ethylene oligomerization, and this ethylene oligomerization came into prominence with regard to the SWAP process, particularly for finding a synthetic route to producing detergents, and this was achieved by oligomerization of ethylene with a nickel catalyst, followed by two other important processes which were added to it. One is ethylene alkene isomerization and alkene metathesis reactions, which together oligomerization, isomerization and metathesis all together constitute the SWAP process, shell higher olefin process, and this was primarily used for preparing the starting material for synthesis of detergents, and this has been discussed in great detail with respect to both ethylene oligomerization as a part of this topic, as well as with respect to olefin metathesis, which was the topic which that was discussed in the earlier lectures. We had also discussed ethylene trimerization, this ethylene trimerization is primarily used to produce 1-hexene. Primarily used to produce 1-hexene using tantalum 3 catalyst, and which was obtained by from tantalum 5 salts by presence of alkylating reagent. And this also we have discussed in great details, particularly the mechanism of its formation, highlighting the main advantage of this process, which is about the selectivity of this reaction. Today we are going to discuss about two other reactions. One is propene dimerization, and the fourth one is cyclotrimerization of butadiene. of butadiene. These two are very interesting processes that we would be talking about today, and both involves a nickel catalyst that carry out these two trimerization of propene and cyclotrimerization of butadiene reactions. So, today's main lecture will thus highlight on these two reactions. One is propane dimerization as well as cyclotrimerization of butadiene. Earlier on in a previous two lecture, we have discussed the above two reaction, ethylene oligomerization using again a nickel catalyst, and second one that we had discussed in our earlier reaction was ethylene trimerization to 1-hexenes using a tantalum catalyst. So, with this we are going to focus on the first reaction, which is propene dimerization reaction using nickel. And this using nickel. Now, this process in which propene dimerizes to give hexenes, various types of branched hexenes, this is called dimer sol process. The process in which propene dimerizes and gives branched hexene. And gives branched hexenes is called dimer sol process. And the reaction is depicted as follows. To N using a catalyst gives where 2N equals x plus y plus z, x gives x moles of hexene of this type plus y moles of plus z moles of now. These are important intermediates. These are important intermediates as they can these branched hexenes can be hydrogenated to give high grade petrol of anti-knock property. Branched hexenes are hydrogenated to give petrol of high anti-knock properties. to give petrols of high anti-knock properties. Now, let us take a look at the mechanism for this dimerization of the propane reaction. The mechanism of it. And that is given as follows. The catalyst precursor is of the type nickel L X type ligand with a allyl. Now, allyl moiety bound to nickel. So, this is a nickel 2 complex, and an allyl moiety bound to nickel can be viewed as such, given over here. One sigma bond, another pi bond, as is the one shown over here, that react with a propane to give nickel X sigma pi complex. So, what really happens over here is that this pi bond of the allele gets replaced by this olefinic pi bond, and this eta 3 becomes sigma and pi over here, as is shown over here. So, now this reacts with an olefin to give this nickel 2 complex X, where this olefin first undergoes migratory insertion into the nickel alkyl sigma bond to give the following complex, as is shown over here. Actually, to be more accurate, these undergoes migratory insertion, and this comes in coordinate, that is the more accurate representation, and this undergoes this to give this inserted complex, which then beta eliminates. This is alpha and beta, and there is a hydrogen over here. Beta eliminates to give the corresponding alkene branched hexene, as is shown over here. and that then reacts with another propene molecule. Again a similar kind of coordination insertion happens, where this insert into the nickel hydride bond and this comes and coordinates to give the product as is shown with a nickel bound now to an isopropyl moiety and an alkene. Note that the isopropyl moiety is obtained by insertion of this hydride into insertion of this into this hydride gives you the isopropyl moiety. Now, the reaction of this with propene gives nickel now again as was observed in earlier case, this undergoes insertion into the isopropyl moiety and this olefin coordinates there, giving rise to this compound as is shown here, and this further beta eliminates to give this nickel hydride complex with alkene, and the product which are formed is this branched alkene as is shown over here. So, trimerization of propane then leads to the formation of variety of alkene through this process as is shown over here. Now, to note, L for the catalyst is phosphine and X is, to note over here that L is L and X are shown here. L is a phosphine and X is a ethyl trialuminum chloride moiety. So, with this we show how this dimerization of propene gives rise to branching branched hexanes, which when hydrogenation gives this anti-knock grade high petrol, and this involves nickel hydride as the active species that carry out this dimerization of propene process efficiently. So, the actual catalyst catalyst is a nickel hydride species the catalyst the one which is eta 3 allele nickel PCY3 Br EtAlCl2, this is the active catalyst, displays high turnover number of around 60,000 per second, and these numbers, the high turnover number is comparable to enzyme activity. For example, catalase exhibits high turnover number of 1 lakh per second. So, this is a interesting compound where nickel is bound to one eta allele, one cyclohexyl group, one bromide, and this Lewis acidic Et3AlCl2, and these sort of is an effective species for dimerization of propane, and that gives various kinds of branched hexanes, which upon hydrogenation gives high quality petrol having anti-knock properties. So, today we have looked into the mechanism as to how this branching of propane occurs, and these mainly go through these nickel hydride active species, then forming the coordinated propane, which then undergoes insertion into the metal alkyl bond to give the branched propane. So, with this we come to the conclusion of today's lecture, which was primarily on this important reaction of dimerization of propane. We had also looked at this reaction in context of the other two alkene oligomerization reaction for Schropp process, as well as these ethylene trimerization reaction to give one hexene. Now, with this we move on to the next reaction, which is cyclotrimerization of butadiene, and we are going to be looking at how this catalyst is used for making this butadiene trimer when we take up the discussion in the next class. So, with that I conclude today's lecture, in which we had discussed about this one particular reaction, which is propene dimerization reaction, and this is called the dimersal process and is used to make branched hexanes, which upon hydrogenated give high grade anti knocking and quality of petrol, and has use in automobile industry. So, with this we come to the end of today's lecture, and I thank you for being with me in this lecture, and I look forward to discuss more on this olefin oligomerization reaction as we meet next. Till then, goodbye and thank you.